Here's a compound inequality. A is less than or equal to 13, or A is greater than or equal to 65. We can graph it as shown. Here's another compound inequality. There's two inequalities separated by the word or, but neither one is solved. So we're going to split them up and give ourselves a little room, and we're going to solve each one. We apply the definition of subtraction on the one on the left. We add 3 to both sides, and then we divide both sides by 2. And we get that A is less than or equal to 8. On the other side, we add negative 10 to both sides. Then we divide both sides by 5, and we get that A is greater than or equal to 11. And then when we go to graph, we remember that it's an OR problem because there are no numbers that are both less than or equal to 8 and greater than or equal to 11 at the same time, but that's okay because this is an OR problem. So there's our graph. All of the numbers less than or equal to 8, along with all of the numbers greater than or equal to 11. Here's another one. We've made a couple of changes. We've added a couple of negative symbols. Let's see how that changes this problem. We split them up. We apply the definition of subtraction. We add 3 to both sides. Then we divide both sides by negative 2, which means we must reverse the sense of the inequality, circled there for emphasis. And then on the other inequality, we add negative 10 to both sides. Then we divide both sides by negative 5. So that reverses the sense of the inequality, circled again for emphasis. And then we remember that it's an OR problem. So we have our smaller number here is negative 11 when we go to the graph, and negative 8 is bigger than negative 11, so it's on the right. And it's all of the numbers larger or equal to negative 8, and all of the numbers smaller or equal to negative 11. Here's a compound inequality that involves the word and. Of course, we didn't need to write the word and because we can write it in this special form. But it needs to be separated like this. The middle part of this compound inequality, the 6a plus 12, it applies to both parts of the compound inequality. So we separate them as shown. And then on the one on the left, we're going to add negative 12 to both sides, which gives us a 0 on the left side. We divide both sides by 6, and we get that 0 is less than or equal to A. On the other side, we also add negative 12 to both sides. And then we also divide by 6, and we get that A is less than 7. And here's our inequality, and there's the graph. All of the numbers between 0 and 7, including 0, but not including 7. Here's another compound inequality. We've changed the 6a in the middle part to negative 6a. We still have to separate it as shown. And now we're going to save some time. We're going to add negative 12 to both sides of both inequalities. And then we're going to divide both inequalities by negative 6 at the same time. And that means we're going to have to reverse the sense of the inequality in both inequalities. So there they are, circled for emphasis. Now let's take a look at what we have. We're going from 4 down to negative 7, which we can write the way we've shown it, where we write the larger number first. 4 is greater than or equal to A, which is greater than negative 7. But when we graph it, we always put the negative numbers on the left and the positives on the right. So on the graph, it starts with the negative 7 and goes up to 4, once again including the 4, but not including the negative 7. This one might be considered a special case compound inequality. On the one on the left, we're going to add negative 12 to both sides, and then we divide both sides by 3, and we get n is less than or equal to negative 2. And on the one on the right, we're going to add negative 1 to both sides, and then divide both sides by negative 4, which of course reverses the sense of the inequality, so we circle it for emphasis. And now we take a look at our graph, and we've marked the negative 2 and the negative 8 in the correct order on the graph. But then we realize that if we start with the n is less than negative 8, we have an arrow going to the left, and then less than or equal to negative 2 also has an arrow going to the left. It's just that that one starts at negative 2. But since this is an OR problem, anything that works for one of the two inequalities is part of our solution set. So it turns out our solution set can be simplified to just plain old n is less than or equal to negative 2. And it turned out the second part of this compound inequality really wasn't even necessary. Here's one where all we've done between this compound inequality and the previous one is change a greater than symbol to a less than symbol circled up there on the top right. And we're going to do the problem on the left by adding negative 12 to both sides and dividing by 3. And then on the one on the right, we're adding negative 1 and dividing by negative 4, which once again reverses the sense of the inequality. So now we have a negative 8 over on the left on our number line and a negative 2 on the right. But we're graphing all of the numbers less than or equal to negative 2 or all of the numbers greater than negative 8. Well, that covers everything on the number line. Some of the numbers on the number line work for both, but every number on the number line works for at least one of these two inequalities. So the best way to handle this is with this capital letter R, which you may remember stands for all real numbers. Here's another compound inequality. It involves the word and, but it's still going to be a special case. We divide it up as shown, and we're going to add 12 to both sides, and we're also going to add negative 6n to both sides, and then divide both sides by 2. On the inequality on the right, we add negative 12 to both sides, add negative 4n to both sides, and divide by 2. And then when we go to graph this, we have a negative 8 and a 12, but we're graphing less than or equal to 12 and less than negative 8. But this is an and problem, so any number that's graphed has to work for both of them. The section of our graph with the numbers between negative 8 and 12 marked with the red arrow, that depicts numbers which are less than or equal to 12, but they're not less than negative 8. And since this is an and problem, while that would work for the graph of n is less than or equal to 12, it doesn't work for both of the graphs, so we can't shade that part in. In fact, we've already colored in the dot over the 12, and it turns out we're going to have to erase that, because a number equal to 12 is not less than negative 8. The only numbers that work for both of these inequalities are the ones that say n is less than negative 8. So once again, we started with a compound inequality, but we finished with a simple inequality, n is less than negative 8. And on this one, we're going to take a look at this and see how this might be a special case. We divide it into our two inequalities separated by the word and on the one on the left, we're going to add 8 to both sides and then divide by 2. And on the one on the right, we're going to apply the definition of subtraction. Then we're going to add 8 to both sides, and we're also going to add a negative n to both sides. And so now we have 9 is less than n, and n is less than 2. Well, 9 is less than n really means that n is greater than 9, which would send our arrow to the right. And if n is less than 2, that sends the arrow to the left. That's fine if it's an or problem, but it's an and problem. There are no numbers that are both greater than 9 and less than 2. So this is a special case problem. It's the empty set. There is no solution to this compound inequality. Compound inequalities involve solving more than one inequality. Solutions of problems involving the word and contain numbers that are solutions of all inequalities of a problem. This is known as the intersection. Solutions of problems involving the word or contain numbers that are solutions of one or more inequalities of a problem. This is known as the union.